So I think we may begin. Thanks for being here. I recall you where we are. In the first lesson, we introduced the idea of the pendulum and the polarities, and at least to begin to think in dyadic terms in which you have enough contrapositions in human thought. And that applied in particular to the main problems of the mathematics and the many possible definitions of mathematics. Then in my second talk, I presented the analytical perspective, one of the sides of the pendulum, beginning with the fantastic principles of mathematics by the young Russell, and then by this unknown professor from Ohio, extremely interesting and very important to know after his lessons. I hope you spread the word. And James Biernishaw, one of the best writers on the understanding of the philosophy of mathematics in the modern period. And then going slowly away from mathematics and approaching more and more of the philosophy of language. Philosophy of language becomes a central, interesting, very important, very difficult, very clever problem about analytical philosophy, but then that puts them away from real mathematics. And in the third session, I presented the other part of the pendulum, in which you have very good either great mathematicians like Poincaré or Grothendieck, some of the greatest mathematicians of all times, in which they reflect very strongly on their own creations, and also some lesser known but extremely important and very interesting French philosophers of mathematics in the tradition of Jean Cavaliers, Rodman, De Saint, Châtelain, Aluni, etc. There is a long tradition of very good French philosophy of mathematics in which the other side of the pendulum is studied with care, in which you go really to look at the mathematics. You look at the mathematics and try to see what is happening there. So here is this pendulum in which on one side, at the beginning, they are very close, but then afterwards, at the end of the 20th century, that they are very, very far apart. And the analytical tradition has concentrated on the philosophy of language, and the French synthetic tradition has concentrated on the philosophy of mathematics. Both of them extremely interesting, both of them extremely hard. But if you are more interested in the philosophy of mathematics, you should be working on the pendulum, not on either side of the possibilities. In particular, something which is very important, mathematics is not a language. Mathematics is usually referred as the language of the cosmos. I think that's a very, very bad idea. Mathematics is something that the human mankind, people have invented through many, many sufferings with their flesh on many problems in history, as we have seen in the beautiful course of the history of paraconsistent logic. Very hard people working very hard and producing a very interesting way of looking at the world, which cannot be reduced to language. Language is a part of mathematics, extremely interesting part, but to reduce mathematics to language is one of the great nonsense of some pendulum. You have to be more open and not to reduce to language. I will insist that today on that today. And the appearance of the paraconsistent logic will be very interesting there. I hope to prove that in a moment afterwards when we advance in our session today. So today I will begin, and I will explore that with a much more care tomorrow. What's happening in the middle of the pendulum between the analytic and the synthetic? At least there should be analytic and synthetic, but in fact, what is really interesting is what's happening in the middle, in which you have an infinity quality of different perspectives. That infinity is really important, and I will stress on that a lot. today I will begin with that, stressing that middle ground. And in that middle ground, we will escape the usual perspectives, the usual analytical perspective or the usual synthetical perspective, and immerse ourselves in very strange minds, but very profound minds. So, in this session, we will be talking about different perspectives in the middle, what I call the devils, the phantasmata, the doings, and paraconsistency. Paraconsistency on the side of the devil, which is the interesting part, of course. The interesting part is the shadow, not the light. Between the light, the supposed analytical light, and the supposed shadow of the synthetic perspective, the one more directed to proofs and language, and the other more directed to creation and imagination, between the two, a lot of things are happening. So let's introduce first, before going to the devils, the phantasmata, and the doings, which will refer to three very well-known philosophers of mathematics and mathematicians for you. Devils will refer to Hermann Weyl, the phantasmata to Kurt Gödel, the doings to someone that is, in contrary, very little known, but I think one of the best philosophers of mathematics in the 20th century, Javier de Lorenzo, great philosopher of mathematics from Spain, and of course, Newton da Costa and his school in paraconsistency. So my presentation of today has this part. First of all, introduce the opening minds, some of the minds which were most open in the 20th century. Minds which are really impressive still today, and for me are like the ideal of what should be a great intellect, a great intelligence, well beyond any particularization, something very, very big, who tries to understand the world in all its complexity. So we will talk about some of these are well-known, other men less. Paweł Florensky from Russia, we will see Florensky, which is extremely little known. Paul Valéry from France, the great poet, but also one of the greatest thinkers of the century. And then something very beautiful which is happening for you young people, which is something that the Czech school invented like 10 years ago, data of transformation, in which the Brazilian output is very important, you will see in a moment. And with that, with those openings, afterwards, we will talk about these great different perspectives, while Gödel, De Lorenzo, and Da Costa, and as before, I will try to make a small map where these things are getting together. So let's begin with Paweł Florensky, almost completely unknown. This person which is there, this phantasmata which is there, Paweł Florensky. Paweł Florensky was, for me, probably without much doubt, the last great universal mind of modern times. He did his PhD in mathematics in the Russian school on problems of continuity and discontinuity. Then he did his PhD thesis on theology. Then he worked a lot as a critic of art. He was a fantastic philosopher, a great semiotician, and a fantastic scientist. He was finally killed in the concentration camps with Stalin. Paweł Florensky is really one of those minds in which the world can enter here. It doesn't happen often. It happened in Florence. And most interesting for us here, it happened in a very strong and very interesting moment for paraconsistency. Professor Gomez has announced that on Saturday he will explain that 1910 was like the annus mirabilis, where you have Lukasiewicz, where you have Vasiliev, but exactly on that time also you have Florensky. And you will see in the papers of Florensky that he was exactly thinking also in paraconsistent terms in a very, very explicit way coming from the greatest school of mathematics in Russia and the greatest school of philosophy and theology in Russia. He was a person who was looking to the very deep things, as Russians do. The Russians are really people who go to the important, dense things. For example, Silver, one of the greatest logicians of today, he goes to the really deep things in logic. Things like that are always very impressive. You know very well the example of Perelman, this fantastic Russian mathematician that solved the Poincaré conjecture. Poincaré conjectures, as Poincaré did, always with mistakes and mistakes and mistakes. Finally, he invented the Poincaré conjecture and solved 100 years afterwards by Perelman, another of those fantastic minds. For me, always the example of what should be a mathematician. The mathematician is interested in the heart of things, going to the profound things. The Russians do that almost better than anyone. It's incredible. And you know that Perelman resisted $1 million. That's something that's an example of a person. And I think that no one of us would have that force, that character force that will say, I don't want $1 million. I want to solve things. So in this fantastic Russian tradition, Florensky is someone really, really serious. Let's read some passages of his PhD thesis in 1914. So very close to the Annus Mirabilis of 1910. This is what Florensky says. Integral truth lies on a forceful contradiction. At the same time, A is A and A is not A. The fundamental part of our understanding. Usually, our understanding cannot be reduced to this stupid law that the things cannot live together. All the time in our life, as was stressed by many of you in the courses and in the conferences, real life is paraconsistent, clearly. But that's not understood by reason before paraconsistency becomes a real logic or a real system and becomes to have a lot of applications in the world. We will talk about that afterwards. Let me see other beautiful quotes by Florensky. As in a shadow, this is the beautiful quote by Florensky. As in a shadow, each sentence is accompanied of the third truth, the side of the contrary sentence. And truth is the unity of opposites, the coincidencia oppositorum. Today, Professor Gomez was bringing into the picture the Cusano, Nicholas of Cusa, the coincidencia oppositorum. This is clear for Florensky, but in fact, behind this, Florensky was, above all, a fantastic reader of Kant. I think the best reader of Cantor who has existed was Florensky. And Florensky read very well the idea of Cantor that you have to work with inconsistent multiplicities, the many which are not one. That was fundamental for Cantor in a moment, and it is fundamental for Florensky. And the idea of an inconsistent multiplicity comes from Cantor. That's the fundamental idea for Florensky. And he takes that as something which should be clearly fundamental for our knowledge. Truth should come from the inconsistency, of the contradiction. So truth brings in her the plenitude of the infinite sequence of her foundations and the deepness of all perspectives. Her abyss is an abyss of potency. Again, you are interested in the deep, you are going to the abyss, you're interested in the potency, so you're interested again in the shadow, in what is not clear. You're interested in the blind spot, in the inconsistency. The term of truth is a triadic relation, an infinite system of acts synthesized in a unity, or better, infinite unique act. And finally, this is very strong, 1914, truth is an antinomy. That's important. Truth is not part of the A and not A. The antinomy is truth. To say that strongly in 1914 is something very, very impressive. And he says, a logical and formal theory of antinomies becomes necessary. That was being done exactly at the same time by Vasiliev, we know, in 1910, and it will be done also with all the care afterwards with the Costa and the Brazilian school. But it was already very present in Florensky. So Florensky is one of the other very fantastic universal thinkers in which you have to understand the inconsistencies to understand the world. If you don't understand inconsistencies, you will lose a lot of the understanding of the world. For him, that was extremely clear. You know that the first paraconsistent logic by Vasiliev was called an imaginary logic, as will be presented in the Saturday session. For Florensky, the imaginaries were also fundamental. He wrote a text which is called Imaginaries in Geometry, in which he takes the basic idea of looking at the plane from the verso and the recto, and with that you have two possibilities corresponding to the two possibilities of complex numbers, and with that you open up the possibilities, the logical possibilities of our understanding. So again, I have insisted a lot of times in our talks before of the importance of the complex numbers in mathematics. They are really fundamental. Without complex numbers, you will never understand mathematics. That was clear for Russell in his Principles of Mathematics 1 century ago. It should be clear for the young people today, even if they are far away from mathematics and restricted to the philosophy of language. That's important. That's important. It's still fundamental. And it's fundamental for people who try to look at the general perspective of things, like Florensky or like Vasiliev, or who are looking for imagination. Let's say, for example, here, the two sides of the plane are intertwined by an impulse breakthrough from the imaginary to the real. So there is an inversion, which will be fundamental in the geometry, and that inversion should invert also the logic. That is what is happening afterwards. We are in presence of the remainder on the real side at the borders of the imaginary. So again, the borders become very important between the positive and the negative. You have a border, which is fundamental, and that border is what is really interesting for thought finally. Here is the beautiful cover for that book, in which you can see quickly, without knowing mathematics or without knowing philosophy or theology, you can see there the complexity of things, which you have to look at the back and the front, and what is happening in the middle. That middle is the interesting part for the very domains of thought. And he has also, I will not insist on that, he has everything that he wrote is fantastic. It's extremely original, extremely original. He wrote a beautiful text on the iconostasis, in which he studied from a critical, art critic and history of art point of view, the icons, and he showed that in the tradition of the Russian icons and in general the Slavic icons, the construction of icons in the culture, perspectives were completely changed. The usual Occidental perspective didn't work. What worked was the conjunction of opposites in the paintings. The paintings were well far away from the clear differences that the Occidental perspective of the Renaissance were trying to produce. In the icon tradition, things were living together. At the same time, and his contrary were living together in the icon. And he wrote a beautiful and very, very fine text on it's a book, an important book on the art of the icons. So Florensky is for me, like the first person here that I want to bring today, in the sense that he's opening our minds. He's interested in inverting our beliefs. Do not believe something. Always be critical with your belief. Think in another way, and perhaps, only perhaps, you will begin to understand part of the problem. Never accept one dogmatic perspective. Always look at the contrary. Always invert. Be extremely critical. Extremely critical, not only of the world, but of yourself, as I was mentioning yesterday. That's one of the powers of introspection of the French tradition. The Poincaré, who is perfectly aware of his mistakes, and thanks to that, he understands how mathematics is invented. The same thing with Grothendieck, that the power of introspection of the French tradition is also something that Florensky had. Go to the deep problems. Another person that I like a lot is Paul Valéry, one of the greatest poets of modernity, you know, but also an incredible thinker in the best sense of the word. Paul Valéry did something, one of these labors that one cannot but admire completely. He more or less awaked all days for 50 years of his life, between 5 and 8 in the morning. All the days of his life, he wrote about how creativity is constructed. And he produced 50,000 pages on creativity. Let me show another example. No other examples are there. Valéry was really a person who had that power of introspection in an infinite way. These are called the cahiers, the cahiers of Valéry. Valéry in the cahiers did this fantastic exploration of how invention was done in every field, not only in poetry, but in mathematics. He knew a lot of mathematics, being a poet and not a mathematician. So you don't have to be a mathematician to understand mathematics. Far from that. You have to be only open enough. You don't have to close yourself in a small part of the world. If you open yourself, that will be very interesting. I will show you just some of the drawings of Valéry, which are very useful for us. This one is a beautiful diagram in which la vie, life, is explained by this simple equation. At the left, the objects and the particularities. At the right, just relations. So life is just relations. The left is just an appearance. To look at how it is constructed this house inside, you are not interested in that. You are interested in how that is related to the world. So I was explaining yesterday that this is the basic paradigm of category theory. Category theory, you are interested in how things are related in the world, and you will understand the world thanks to the relationships between things. Not going inside the things that usually you cannot go. And for me, the best example always is ourselves. Except if you have an incredible power of introspection, except if you are a Valéry, or if you are a Grothendieck, or if you are a Valéry, usually we don't have that power. We don't know ourselves, but more or less we behave in society. More usually with difficulties, but we try to live in society. Diagrams in that sense. To understand the spirit has a lot of currents, positive and negative currents. You navigate between the different currents. For those who know your Riemann surfaces, you have here a Riemann surface, 1899, drawing in which Valerie is in fact using English here, in which you can see sound, sight, and word. You have some of the different constructions of the language. Those different constructions of the language are connected, the ones with the others in different planes. I will come back with this with force tomorrow. For me, Riemann surfaces will be the key to try to understand at least a little what is happening in the philosophy of mathematics. But it was clear in Valerie. For Valerie, the fight between the real and ideal is fundamental, and then you have to navigate between the different islands into the real and the ideal. Here you have also a way of drawing life. Life is complicated. Life should not be restricted. Life should not be restricted to a plane, but at least to begin to have a small geometry in which things are a little more complicated, like the Möbius band there that is inserted the one to the other, or diagrams in which the self-reference is fundamental. If you want to understand something, usually you have to be aware enough of yourself. The serpent. Yesterday in the beautiful, very beautiful, extremely beautiful film on Newton da Costa said the important thing is to throw serpents in order that the people become aware of some peril around you. You should never be happy with yourself or happy with the community. No, throw serpents. It's here. By the way, I was a little sad yesterday that I saw that in this beautiful film that should be an example for all young people, there was less than a third of you looking at the film. That was, I didn't, was very happy about. And ramifications. The idea of ramifications are really fundamental. Never accept a linear perspective. Always diversity, all the time diversity. Never accept one way, never. Beautiful drawings about philosophy and music. Yesterday, Trevisan proposed a fantastic reading of connections between logic and music. Guerino Mazzola, perhaps the greatest theoretician of music of the last 30 years, has worked a gigantic work of the connections between mathematics and music, the famous topos of music. It's in his third edition, now it has like 3,000 pages. People who really work, Valerie, Mazzola, etc., should be great examples for each of us in which we are very, very far away from them, but at least we should know that we are very, very far, and we have to do very small steps to go beyond our human condition. What is our human condition? Very simple, ignorance. Yes, that's the human condition. The human condition is ignorance. And yesterday, Professor da Costa, in the fantastic film that you must see, I hope that it will be repeated next week or something, Professor da Costa insisted that for him the important thing was knowledge. Go beyond our ignorance. We are ignorant, horribly ignorant. But we should be aware of that condition and then go against us. Be extremely critical, our stupidity. These people are all looking and working all their lives against the stupidity. The Atlas of Transformation, closer to us, a group of incredibly fantastic young Czech philosophers which have done a web of connections around the world, very, very beautiful, in which they have studied very well the idea of the transit. I have insisted several times, what is the prefix of our times? It is not in, it is not out, it is trans. It is the border. What is happening in the border? That transit is driving all the work today, should be driving all the work of the young people. And this school, the school of the Czechs, have done that very seriously. They wrote a gigantic Atlas of Transformation, very, very beautiful, in which they draw fantastic diagrams, and with those diagrams, they are able to produce good maps of the complexity of our times today. So here you have the Czech school in Prague, 2010. The basic desire is this one, to understand transformation. Transformation signifies alteration, then you have to alter something. Transformation is only possible through disintegration. You have to break things. Our knowing is a constant search for a delicate balance between local and global, without one ever being able to annihilate the other. Local and global, by far, one of the most important problems of mathematics since Riemann to today. I will insist a lot on that tomorrow. Local and global shifts, that's the work of shifts, to understand what's happening with local and global. In order to be able to orient ourselves in the realm of transitions and metamorphoses, we need imagination again. Without imagination, forget to understand the world. You have to go to the imagination, to the ideal, and then that will help you, perhaps, only perhaps, to understand the small parts of the world. But you have to go to the imagination. You have to go to the complex numbers. You have to go through Vasiliev's imaginary logic. You have to go through Florensky's imaginary understanding of the iconostasis, etc. Imagination. Without imagination, no understanding of the world. Without imagination, no understanding of mathematics in particular. No way to understand mathematics without imagination. Here you have a beautiful drawing by Ricardo Basbo, an artist from Rio de Janeiro, in which he participated a lot on the Atlas of Transformation. You have this beautiful diagram in which you have all kinds of different connections, for example, between thought and body, the importance of friendship, me against the you, the never and the no, the here and now and better, the there and the beyond, etc. Lots of connections in the world. Those connections are related to hybrids. Hybrids is also something fundamental for the understanding of our world. Margins, inversions, to resist. We will talk about resistance in a moment. To resist. Mathematics is one of the best inventions of the humankind to resist, to go against supposed truths. The mathematician always is questioning something. He is questioning every time everything. In order to produce some kind of harmonization, some cohesion, some synthesis, and in the middle one, producing some kind of crossings and mixings. Here you have another beautiful drawing by Paulo. We have the transformation where it's nice, very nice to find this in Portuguese. Okay, with this long introduction, but I think it was important, we can now enter to the philosophers of mathematics. The first one is Hermann Weyl. So Hermann Weyl, 1927, his book on the philosophy of mathematics and natural science. Hermann Weyl comes from the big German tradition, the fantastic tradition of Göttingen, Riemann, Dedekind, Hilbert, the very great, fantastic mathematical traditions of the 19th century in Germany. But then he had this wonderful opening that beyond his master Hilbert, he did his PhD with Hilbert, beyond Hilbert, he was interested and extremely open to what was happening in his time, and he became an adept of Brauer. Weyl becomes one of the first good, profound connections between what is called formalism and intuitionism. You should take these things and throw them to the garbage, and particularly when you have hundreds of pages on that, throw that to the garbage. It doesn't make any sense today. It perhaps made a little sense in a moment, but just for the philosophers, for some philosophers of mathematics, the mathematicians were never interested in those foundations. They did their mathematics very well, no problem with foundations. The problem of foundation was something imaginary, very interesting, an imaginary construction of some people. But Hermann Weyl connected Hilbert and Brauer. We will see in a moment of another one who went even beyond that first fundamental connection between Hilbert and Brauer. The idea of, the basic idea of Hermann Weyl is again very profound and very simple. He was a very strong mathematician. He was the first one who produced the model definition of a Riemann surface in 1913. The Riemann surfaces come from Riemann's PhD thesis in 1851, a very difficult text, and you have to be very patient. But if you take some days to read part of it and you finally understand some paragraphs, it will change your life. It's true. Riemann surfaces are really incredible, and if you go back to the sources, as I usually recommend, always read the masters, not the secondary or tertiary literature, always read the masters. While read the master, read Riemann, and he produced the modern definition of a Riemann surface, which is extremely simple today. It was not at the time of Riemann. Now, the Riemann surface is something very, very simple. It's just a complex variety of dimension 1 over the complex. That's it. So it's a surface in which locally you are living like in the plane. That's it. That's the Riemann surface. And we will use that very simple construction tomorrow in order to try to encompass all the different perspectives that I am introducing in these first 4 lessons. The pendulum was fundamental for Weyl. He was very eager and able to work on ideal mathematics, but also he was very interested in the real, in the physical world. The back and forth between the ideal and the real was clear for him, and also something more of his kind. He introduced this basic and fundamental duality between algebra and topology that was invented essentially by Poincaré with his algebraic topology. It's 1890 to 1905, the algebraic topology of Poincaré, and then Weyl, some years later, puts these two as the board of the as fundamental polarity of mathematics. He calls algebra the devil, so that's why we are talking about Hermann Weyl's devil, and topology as the angel. Why so? I think it has been clear in the many courses that have been presented. Algebra is more related to calculations, to language, to equations. Topology is more related to forms, to a kind of continuity, to a kind of softness. Softness was mentioned today by Gomez, in a moment when he talked about the idea of Leibniz. Reason should be soft. Softness of reason. That's what we called in our first session the razonabilidad of Vaz Ferreira, the master of Joaquín Torres Garcia, who will come again today in a moment, and who was presented by Marcos, which is shared in the first lecture. So we're interested in soft reason, not a reason which puts walls in our understanding. We want reason which helps to transit between the many differences in the world. Soft reason. That soft reason is captured by topology. Topology captures softness. That's why for Grothendieck, topology will be fundamental. If we can say in the history, I am now talking about the history of mathematics from Archimedes to today. Who was the greatest mathematician who understood softness? Alexander Grothendieck. Everywhere in his work, you have softness. Softness to understand spatial vectorial topology, softness to understand abelian categories, softness to understand Riemann-Roch, softness to understand something which he invents, which is the inverse of the algebraic topology of Poincaré, the topological algebra of Grothendieck, in which introduces soft tools to understand algebra. So we can understand why. It's of course it's a calembour, and it's a kind of aggressive introduction of a polarity, but it's a polemic which is extremely interesting. Introduced that polemic in the article on invariance in 1939. In the middle ground between algebra and topology, the master. I hope that after my lessons, it will be clear who is the master of mathematics. Riemann is the master. There is nothing to be done. He's really the greatest mathematician, clearly the greatest geometer of all time, and probably one of the greatest mathematicians of all time. So this search for topology, for the angels, is very interesting. Also, on one side, on the side of the angels, you have Paradiso. On the side of the devils, you have Inferno. Between the Inferno and the Paradiso of Dante, we are there. Our Purgatorio is our life. Of course, of course, it's clear. The Purgatorio is our life. And we want, in a sense, to escape our horrible human condition, ignorance. We have to escape ignorance. How? Going at least to trying to approach some enlarged reason. We will talk about that with Costa. Some enlarged reason, which goes beyond separations. Looking for something plastic. Something plastic. We do not want taxative separations. I would say that, again, these things are very personal, but a taxative separation shows little intelligence. Little intelligence. If you want to go in the approach, some kind of a small intelligence, you have to go away of the words. Today also was presented by Gomez that in the beautiful quote on Cusano, we have to escape the words in some sense. So Hermann Weyl introduces this very, very nice idea that we should be interested in the back and forth between the devil and the angel, between Paradiso and Inferno. And now we introduce the infernal one. The infernal one is this guy. The photo is fantastic. That is paired together. The greatest logician of the 20th century, probably one of the greatest in history, one of the greatest analytical minds. Fantastic. But he was well more than that. But he was extremely well known for his work when he was very young, between 25 years of age and 35 years of age. Or again, as happens all the time, with Florensky it was the same. His PhD thesis at 30 years. 30 years seems to be, and it's fantastic for you young people, like a very good moment in your life, very good moment. Have to profit from that. For Gödel, it was like that. In between 25 years and 35 years, he invented and constructed some of the most impressive theorems of the 20th century logic. Of course, completeness in his PhD thesis, completeness of the first order classical logic, his famous PhD thesis, 20 pages. But exactly at the same time, you go through the manuscripts in the history of logic. It's very, very beautiful. Again, I recommend go to the sources. Go to read directly Gödel. Go to read the sketches of the proofs that he's writing at the same time. One can see exactly at the same time that he is proving completeness for first order logic and incompleteness for Peano arithmetic. What we call Peano arithmetic. In fact, you know, incompleteness for a system of arithmetic coming from Principia Mathematica of Russell and Whitehead. And that's the reason that why that book changed the history of logic. No, not because it produced a proof of logicism, but because it was read by Gödel. Thanks to that, Gödel then produced a beautiful axiomatization of logic and was able to construct and invent one of the most beautiful constructions of mathematics in the 20th century, which are the recursive functions. The recursive functions by Gödel are the basics. You know that much better than me of all our computing world today. The most important part of the proof of the incompleteness theorem by Gödel was to show that the predicate of proof is recursive, but not primitive recursive. He invented the difference, and he showed with, I think, his 60 formulas. In the 60th formula, he showed that the predicate of proof is recursive, but not primitive recursive. And with that, he shows, taking the negation and a fixed point in the diagonal, that there are sentences which cannot be decided by the system. That was the great power of a fantastic analytical mind, resolving the most important logical problems of his time. Very, very fast, in 2 years, working on them at the same time. And then afterwards, that's finally done in between 29 and 30. Gödel is interesting historically. Gödel finally did not complete his proof of incompleteness. It was von Neumann who finally got the final proof of incompleteness using some model operators. But after that gigantic effort, Gödel began to look at the connections between intuitionism and classicism. And then he has his beautiful series of papers on intuitionism between 1931 and 1933, in which he shows that they are equiconsistent and a lot of other things, the model interpretation related to intuitionism, etc., always with the legendary concision of Gödel. Very short proofs, going directly to the bottom of the things, to the profound part of the things. And then in 38, after some work, he produces famous consistency of the continuum hypothesis. If the world of sets doesn't grow too fast, if we are in a constructible world, then the continuum hypothesis doesn't explode, and the size of the continuum is, in fact, the next size after the natural numbers. That's what we could call the positive side of the Gödel related to the light, to the clearness. But then, that's 38, then Gödel lived until the 70s. There are 30 years afterwards, after that. They are completely erased in the history of logic. Why? Because it doesn't fit the usual narrative on the analytical tradition. It goes very, very way, far away of the analytical tradition. It is not well accepted, but it exists. Let's look a little at that. This is the understanding of the philosophy of mathematics by Gödel in the 50s, in which there is a pendulum between empirism and Platonism, between the real and ideal, matter and spirit, between the positive and the negative, the incomplete and the complete. I put the incomplete on the left side because it's considered as a positive thing, but Gödel, as the genius should do, never believed in his proof. He really thought the incompleteness is a phenomenon related to some kind of axioms, but in fact, what we need to do is, since we are incapable to prove completeness with these axioms, we should introduce new axioms and extend our hierarchy, and then, in some moment, we will have completeness of a higher order. That was the goal. And Gödel puts a very interesting fight between the two. The Platonism, which is something forgotten in the 20th century, and instead the empirism tendency is very, very strong. And he says the spirit of the epoch is to go to empiricism, forgetting this idea of Plato's. And he says mathematics should be recalcitrant. Mathematics should revolt itself against the spirit of the epoch. Mathematics should be and is a revolutionary thought. The mathematician is a mathematician if he is revolutionizing things. If not, he will not be a mathematician. Will be something else. The greatest mathematicians are always trying to go to new things, this kind of imagination, this resistance. That's why it happens a lot of the time that the person, the mathematician as a person, tends to be a revolutionary, an anarchist. The greatest case, Grothendieck again, the example of the anarchist, against any system. And one of the first people who really took care of the ecology of our planet. And in the going the back and forth, what is interesting finally are what I call it the fine path along the borders of inconsistency, which was also the fine path for Cantor. For Cantor, the path between the many which are one, the good sets, and the many which are not one, the inconsistent multiplicities, that was a very interesting path. I showed very quickly, but it could be shown with precision. If you have enough inconsistent multiplicities, you have a path, a very interesting path, to prove that every cell can be well ordered, which was central for that. So he had this brilliant idea that the inconsistency will be the heart of the set theoretical work. Very, very important thing, which has been forgotten. And beginning to approach stranger and stranger things, Gödel had this idea that there is a seer inside us, which is beyond our usual eyes. There is something beyond. It was called a beryl this morning by Nicolas Dacusa. There is a long tradition from what we could call negative philosophy, extremely interesting tradition, in which we are blind. I said the fundamental part of the human condition is ignorance. Yes, but also blindness. We are blind. We don't know how to see. We think we see, but we are not seeing. We are very, very blind. That's something important for poetry, extremely important for films. Tarkovsky, he insisted a lot of times, we are not seeing. I am inventing images to show things that we are not seeing. Our blind eyes prevent us to understand the world. We are blind. So there is something more beyond. And for Gödel, it was like a third eye, this beryl of Nicolas Dacusa. And in that line, looking and looking, Gödel, for years, many, many years, many notebooks, he wrote things which are very, very strange to us. I will read some of them. They come from this wonderful study by Pierre Casanogues, Le Démon de Gödel, has been translated into English. Casanogues is one of those philosophers of mathematics of the great philosophical tradition of French mathematics. He went to the archives of Gödel in Princeton, and he took the care for 2 years to read carefully what is not shown of Gödel. What the edition, the traditional edition of Gödel collected works, beautiful edition, 3 fundamental volumes of the finest logical tracts, 2 volumes of correspondence, and nothing, absolutely nothing, of the hidden Gödel. Why? It's on purpose. They are not interested in showing that Gödel was not just the good analytical philosopher, he was something much more complex. And the things that I will read are really, really, really surprising. Let's see a Gödel. This is Gödel talking. Gödel said, what happens in the soul possesses the same degree of complication than the entire world. This is this great tradition of the hidden negative understanding of things, the Leibnizian soft reason. It would be interesting to model a system of false but stable beliefs. Mysteries are meant to see by analogy what is exterior to perception. In mathematics, we have to discover what we may be produced unconsciously. This line, this important line of Poincaré, in which the unconscious is fundamental to create mathematics, is also repeated by Gödel very strongly, but even worse. In this life, we never enter in contact with reality. Beautiful. That is said by the greatest logician probably of all times. In this life, we never enter in contact with reality. So I come again to that fantastic definition by Russell of mathematics. The definition of Russell by mathematics. Mathematics is the science in which we don't know what we are talking about. Completely true, because that's what does mathematics, to go beyond the reality. There are other worlds and rational beings of a different higher species. So Gödel, the great rational analytical mind, is saying there are other species. The world in which we live is not the only one in which we will live or will have lived. Something very, very natural for many philosophies. Oriental philosophy is very, very natural. It could be perfectly. Why the Orient, the Occidental tradition should be? We see like a blind person, or like through an ear. That's better. How do we see? Through an ear. So we don't see anything. Our evidences contradict each other. So contradiction, finally again, fundamental. Said by Gödel, the greatest rational, analytical mind of the 20th century, probably of our time, had a complex world behind him. Never accept one perspective. Never accept one perspective. Let's continue. I have to go a little further to have a little time to talk about Newton. I will go faster on De Lorenzo. I think that De Lorenzo is also a fantastic philosopher. I just will mention 4 books of him in the 70s. Introducción al estilo matemático, la filosofía matemática de Poincaré, always there. Riemann, Poincaré, Galois, should be always there. La matemática y el problema de su historia, el método axiomático y sus creencias. Beautiful 4 books in which he insisted on something very, very important, I think, for each of the mathematicians in the history, is that the mathematicians have their style. They are inventors, they are creators, so they have a style. If you read Galois and if you read Riemann, they are very, very different. If you read Riemann and you read Poincaré, they are very, very different. If you read Hilbert and you read Grothendieck, world apart. Why? Because each one has its own style. The style is fundamental. If you are inventing things, if you are creating the world, then you are introducing a style, a way of thinking and a way of writing. Both of them are important, extremely important. And he insisted, I think he's the best philosopher on that side, on the importance of the style in mathematics. And he has a beautiful ideas in which the style is related to the action, much close to parts of Wittgenstein in one moment also. And that is like, this is in the 60s, 70s, well before what is the fashion today of what is called the philosophy of mathematical practice. I think that's important, because it's also a reaction against some philosophy of language, against some synthetic philosophy, against the philosophy of mathematical practice. It's a good part of the understanding of mathematics, but it was done by De Lorenzo 40 years before, and much better than the practitioners or the philosophy of mathematical practice today. That's something that I will always try to stress, and it has been very well spread in the course on paraconsistent logic, in which the fashion of the moment has always, beyond that, a long and important history. So let's arrive to la Costa. Sistemas formais inconsistentes. in this part that I want to call the approximation of the shadow, the approximation of what is finally interesting, the approximation of the devil, of Gödel phantasmata. That's the part which is more interesting and which is more related to creativity. In a moment, I will try to draw a diagram on that idea. Sistemas formai inconsistentes. The PhD thesis by Da Costa, 1963. It has not been stressed yet, but it will be stressed, of course, Saturday. We are not only celebrating 93 years of Newton da Costa and 40 years of Clé, but we are celebrating most especially 50 years of his PhD thesis. That's an important year. 50 years ago, Da Costa produced his PhD thesis. 60, sorry. Thank you. Very, very interesting, and how time again has the moments, the development in the history of thought. So I will insist on some of the things that were done yesterday, said yesterday by Da Costa in his film. So I will profit from that. First of all, a quote which is very nice and very typical of Professor Da Costa: "The highest power of human reason seems to be obtained when it approaches the danger of trivialization." So the highest power of reason is when you are near the abyss. We talked about the abyss with Florensky. If you are near the abyss, we talked about the inconsistent multiplicities of Cantor. If we are approaching the inconsistency, there you have the highest power of reason. The small power of reason is to produce the walls, the simple walls of the world, the simple compartments, the simple truth tables. Those are very, very bad ideas. Important for logic, not important for the world. Yesterday, Da Costa in the film insisted that for him, the goal was to understand knowledge. Again, in my perspective, that makes sense because we have to escape our condition. Understand knowledge. So reconstruct dialectics. Dialectics with an S, as was taught today by Professor Gomez, the dialectics of Hegel and Marx. Fundamental for Da Costa. That reconstruction of dialectics was clear for him. The idea that the horizons are blurred. We have not well presented horizons. The horizons are vague. That horizontality is fundamental for the understanding of the world, for the understanding of our reason. We have to, in a sense, and very close there to the Santi, I don't know if Da Costa knows the Santi, probably not, but very close to the stratified horizons of the Santi that I was presenting yesterday. Of course, understanding uncertainty. So you have to understand what escapes usually your space. The global and the local. The fight between the macro universe of relativity and the micro universe of quantum mechanics. How can you understand that fight using paraconsistency? And he insisted several times in the film, one of the fundamental goals of our being in the world is to enlarge reason. Enlarge reason. Reason cannot be bound. You have to enlarge reason. I call that, with Vaz Ferreira, to enlarge the sense of our rigid constructions. Mix together reason and sensibility, rationalidad, to enlarge reason. That was presented here. to enlarge our world. How can we enlarge our world? With at least beginning with Torres Garcia drawing presented by Marcos, you have at least to invert. The north is the south. At least to invert. And then you have to begin to pendulate between them. At least. You have to invert, and then you have to look, in a sense, to try to move things, to produce a dynamic reason. That was something that Costa insisted a lot. We need to introduce a reason which is dynamic, and then which can be propagated to the world. It has happened. This is our actual perspective now. Para consistent logic, going through all the world, the magnificent symposium here organized by Professor Ottaviano, in which you have students really from all the world, something fantastic, and which is really changing, of course, our mind, and I hope it will change a lot the mind of the young people. That's why I was very happy that many of you were not here yesterday looking at the master. Again, I always say this, a professor is important not by the amount of information that he provides or she provides, but by his or her example. You look at Costa, oh wow, that's an example. We are very, very far. That's an example. Then you have these beautiful things that are happening in this encounter. The book by Gomez and Ottaviano, in which you have the history of paraconsistency, and finally arriving Saturday on the Costa. And a very complex history, you saw, with all these transitions, extremely interesting transitions, as Professor Ottaviano mentioned several times, the importance of medieval logic as a transition. The medieval logic seems to be really one of the great moments. But I would say also, and it will be clear on Saturday, 1910, the transition of the Russians and the Lukasheviks. Something strange was happening there. It's strange that Poland and Russia are both understanding something really seriously in that moment. I think that we have 3 Russian students here. I don't know if they are here, but they are in the symposium. They should study that in the manuscripts directly. Why Vasiliev, why Florensky at the same time in Russia? That's a very, very important research to be done. That's from the perspective of the history of something which is extremely complex and extremely interesting, extremely big. But then you have also the techniques. We will have the course by Cornelio next week, and we are having the course by Carnielli now, the real handbook of paraconsistent logic, something that should be called the handbook, not like the other. This one is really a very good handbook. And there is this idea that we have to go to navigate, to free ourselves beyond the safe Mediterranean. We have to open ourselves to a wild ocean. That's why the metaphor that Gomez and Ottaviano took beyond the Pillars of Hercules. Pillars of Hercules was one of the entrances of the Mediterranean world in ancient times. So beyond the safe things, we are interested in the wild things, the ones which are really, really strange and very interesting on those perspectives. So here I want to draw a small diagram. Which is related to what I would call the fundamental problem in the philosophy of mathematics. The fundamental problem in the philosophy of mathematics is to try to understand, or to begin to understand, how is it possible that mathematics, which is a historical construction done by hard-working men and women along history, with a lot of efforts, a lot of suffering, how that is stable. Galois, Riemann, very different people, Hilbert, Archimedes, Grothendieck, why those constructions are still today stable. That doesn't happen in any other field of thought. It only happens in mathematics. Mathematics is stable. It's a universe, an architectonic universe, in which independently of the foundations, but I should draw it very differently. Instead of those foundations that we usually draw, there are no foundations, but there are a lot of very interesting paths in the architecture and in history, something which is invented in one moment, other moment, finally enters into the architecture, and here we have some which is stable. When here we have something which is dynamic, vague, obscure, etc. Fundamental. I have insisted on the fundamental part of obscurity in the mathematical world. You need to have some kinds of shadows, the Gödel Phantasmata, the devil of Hermann Weyl, the styles of Javier de Lorenzo, the contradictions that Costa opens up for our world, etc., etc. These obscure constructions, in some moment, they become stable in the architectonics. Why is it so? How is it possible that happens? That's a fundamental philosophical problem. I would say the most important problem in the philosophy of mathematics. How is it possible that mathematics, which is a construction of the human mind, becomes stable to civilizations? The only construction which does that. It doesn't happen in philosophy. Clearly, you would never say that Quine is more important than Plato. Never, never. You can say very easily and prove it that Riemann is more important than Archimedes, that Grothendieck is more important than Riemann. Those things can be shown, proved, because there is an architecture which is stable and which captures the things which come before and which grows. There is this famous statistics that Dieudonné, one of the writers of Bourbaki, did in the 60s. John Dieudonné, one of the founders of Bourbaki and the writer of most of the treatises of Bourbaki. Dieudonné did a beautiful and very shocking statistics in which he more or less proved that 90% of the important mathematics that were done in his time, which was in 1960 and 1970, were produced in the last 20 years of his life. So much more mathematics, much more important, much more profound than all the history of mathematics. There's something very strange that happens in mathematics, and it is something that we should care about, because our time, not the time of Nicolas d'Acusa or Ramon Llull or Plato or Leibniz or Archimedes, our time is the most exciting time for mathematics. So it would be kind of a pity that the young people are not present in our contemporary world looking to the mathematics that are done today. Very, very important, very deep. Why is that so possible? I think I have a small hypothesis on that. Looking at what has been said in the different courses, not in my course, but in other courses and other perspectives, in which we have this pendulum. The pendulum between the light and the shadows. I should put it in the other way to accord with this. Here we have a pendulum also, an stable part and unstable part. Here we have the shadows. Here we have the light. Here we have the supposed clearness. Here we have vision. Here we have plasticity and dynamics. This is related to what is very, very important in mathematics, which is creativity. And this is related to the other part, which is extremely important also. You cannot stay here or there, which is proof. This is more mathematical. This is more logical. But there is a back and forth between them. Fundamental back and forth. You cannot stay there. You cannot stay on the right or on the left. That's fundamental to understand what is happening there. And it was mentioned today by Carnielli, and I agree completely with him, that mathematics, this edifice of usual stable mathematics, the one who has been steady through the ages, from Archimedes to today, that world doesn't need paraconsistency. Here, everything works extremely well with classical logic. You don't need paraconsistency there. The mathematicians are in this part of the proof of the world, the architectonics. The architectonics, which is stable through the ages, classical logic is enough. Perfectly enough. It works very, very well. And even I would go even beyond. The mathematician does not need logic. He just needs structure, beauty, coherence. He needs to go to the profound things, and with that, he or she will be happy. Going to the deep, to the abyss, that will be close to mathematics. And then afterwards, it will enter, after being in the abyss, it will enter the architecture. It will enter here. And then it will become stable here. What is interesting, I think, is that on the left, it is very, very natural to think paraconsistently. Here, the paraconsistent logic is, I think, where it becomes useful in the philosophy of logic and mathematics. Why? Because the paraconsistent logic really understands these things. It is the logic who really understands plasticity, who really understands that we need, in order to invent something, come from a contradiction. In mathematics, not a logical contradiction, but the contradiction between algebra and topology, the contradiction between the devil and the angel. Those contradictions are fundamental for mathematics. And with that, this part will be better understood. But often what happens is that when we think mathematics, we think only on the right side. Great mistake, big mistake, typical mistake of the analytical philosophy. They look only here. That's completely crazy. It doesn't make sense. It's important, extremely important, but it's just a small part of the work. And in that part, in this one, paraconsistency would be, is my hypothesis here in the different courses and conferences, that paraconsistent logic can be in the field of the philosophy of mathematics extremely important to understand creativity. It is not useful to understand the architecture of Riemann, but it is fundamental to understand how Riemann invented that architecture. It's the only way. And that was extremely clear for Florence. I am quickly finishing. Let me draw this final diagram. All of these diagrams are on my page already. In the academia, you can get them there. This final diagram opens up this dialectic. On one side, what is the usual perspective? Light, objects, angels. But we are interested, personally, I am more interested in the other part. In the penumbra, the phantasmata, and the devils. Those things are very, very interesting for mathematics. And those are related to creativity at large. Of course, it is interesting, and it has been done a lot, to understand the architecture of mathematics in the stable perspective. But the other one is at least also of the same level of importance. Personally, I think it's more important because this is related to the other fields of great creativity, to art, music, literature, as I will show tomorrow. They are very, very close. Mathematics is very, very close to other fields of invention. So that this part is very interesting, and the plasticity of paraconsistent logic would be there a very good tool, very nice tool to understand things. And that's one of the goals of the Costa. We want to understand knowledge, the complexity of knowledge, the plasticity of knowledge, and if we are able to use paraconsistent logic to understand the fundamental drive of the mathematician, which is to create new things, that would be interesting. So on the top, you would have the paraconsistent logics. On the bottom, the subintuitionistic logics, which provide you the light of the architecture, and here something more plastic. And in the middle, what I have been calling for a while now, and this is something that I would try to write very carefully. I have been working on this for several years, but I haven't been able yet to write the book that I want, is to produce systematically something that I have been calling orotics. Between the analytics and the synthetics, there should be a science of the border, of the frontier. What happens in the middle? Oros means in Greek border. Orotics, has it existed? No, it hasn't existed as a systematic science. It should. It's extremely important. If we had at least a beginning of orotics, the world will be much better understood. I think it's fundamental for our world, fundamental for young people to understand the borders, the transition, to go against analytic and synthetic, and in the middle, you are going beyond restrictions, and you are approaching life, which was the goal of the master Newton da Costa. Thanks. So if you have any comments or questions, yeah.
I have a quick question about your lab diagram. In the right side of your diagram, could you substitute the word proof by rigor? If rigor, if not, but why?
Okay, good. Extremely beautiful and important question. I would say that rigor is here. Because rigor is not just formal rigor, to be here, but informal rigor also is extremely important. Informal rigor. And here you have in the line of the informal rigor, you have, for me, the greatest masters of modern mathematics, which are Galois and Rigor.
I think that notion of crisis, the defender of the text, informal rigor is proofs.
Yes, the informal rigor is extremely important, and the formal rigor is more akin to proof. But this part is really fundamental. You cannot talk about the genius of Galois, the genius of Riemann, without this idea. They were extremely rigorous for what they were looking. They don't need or foundations, or logic, or even proof, or even definitions. You look at the Riemann thesis, 1851, there is no definition of the Riemann surface, of course. No definition, no proof, nothing. Ideas. Representation theorems, not entirely proved, with a lot of gaps, just solved 60 years later by Poincaré, the famous uniformation theorem by Poincaré. A Riemann surface which has no holes has only three possibilities. It's either the sphere, or the disk, or the plane. Famous, very important uniformization theorem by Riemann, stated by him, not proved completely, just by Poincaré 60 years later. Things like that happen all the time. The informal rigor, I would say, very important for mathematics, extremely important for mathematics. Much more than this becomes to be very important afterwards, after Hilbert says. But before Hilbert, it didn't make sense. For the very Poincaré. In Poincaré, you have proofs with a lot of gaps. Dieudonné, who was the writer of Bourbaki, an extremely rigorous person. If you have read Dieudonné, I would recommend the Le Monde d'Analyse de Dieudonné. Dieudonné was in Brazil also. The Le Monde d'Analyse de Dieudonné, an 8-volume encyclopedia on analysis of modern analysis, everything perfectly defined, proves completely correct to the end. Dieudonné said about Poincaré, I cannot read Poincaré. He was horrified by Poincaré because the proofs are completely different. Here in Poincaré, the informal rigor is fundamental. For Bourbaki, this is anathema. You cannot talk about this. You have to be extremely formal. Bourbaki is extremely formal. Very good, extremely interesting, but just a part. Thanks.
I have essentially two questions. The first is, I was thinking about they have a role within mathematics, not within mathematics in development itself, but within mathematical communication. I mean, within the community of mathematics, you see an article in mathematics often has to use some theorems to start the development or the creation. And you see a link to an article in which you have this theorem and it has to be proven, so it will have to be legitimate. So it's or the creation needs the proof on that article. So either this theorem is proven Or it's not, do you see this role in communication?
Yeah. Yeah. So to the first question, absolutely. So that I have insisted a lot that the two parts are fundamental. You cannot stay here or you cannot stay there. The two parts are fundamental. And particularly with the standards of formal rigor after Hilbert and Bourbaki. Not before, but after Bourbaki, then you have to prove everything. You cannot just publish an article in mathematics in which you put, these are the ideas. It will not be accepted by the community. The community now has the standards of proofs. It's fundamental for the communication, as you say, because then the community can check if the proof is interesting, if there are ideas in the proof, etc., etc. Those things are really something necessary. But this part is the one who is behind the proof, and which is also extremely important.
And also about paraconsistent logic more directly. If you have a paraconsistent logic on the other side, the creativity part, of course, has a lot of inconsistencies because you stumble them about all the time when you're developing. Sometimes if you have a paraconsistent logic on the formal side, you may, to use an image, swing the pendulum before. In general, in a classical framework, you would have to resolve this inconsistency before you can swing the pendulum.
Okay. Yes. Here in this part, and we have had extraordinary and beautiful experience of that with the course of João Marcos and with all the work of Carnielli and Cornelio. Here in this part, you have paraconsistent systems completely formalized. Very good, extraordinary formalizations of paraconsistent perspectives. Beautiful logical problems and beautiful models for those problems, algebraic perspectives, topological perspectives, everything on that side that's here. It works perfectly well in this side. But what I am saying is that independently of that, which is one of the main developments of consistency, is to formalize seriously with a lot of work, very different perspectives, very different systems of paraconsistent logic. Independently of that, you could use paraconsistent logic as a meta-logic to understand creativity here. And Carnielli said it clearly this morning. In the meta-logic, to understand this, the meta-logic is always classical. Always classical. And the beautiful models come from Fichte models. I will be talking about on Fichte models tomorrow. Metalogical constructions in which the classical metalogical language is fundamental to understand this construction. Okay. Here we are proposing something very different. Yeah.
Well, I think that at the core of the analytical movement, you have logic and everything around it. And for me, also at the core of the aesthetical movement, 1990s, you have category theory. So I think maybe, I think that in the future we need to the synthesis of this, right? And would be applying category theory to logic and vice versa.
It has been done. Well, one of the interesting things of the school of Lovier in the States and the greatest school of Canadian logic in the 80s is to use category theory to understand all the layers of logic. It has been done very well for categorical logic. It has been done very well.
Yep. Evandro is asking me to close the session.
Yes.
This is fantastic, spectacular. Thank you, Professor Zalamea.
A pleasure.
Thank you for the brilliant class.
Thanks.